Just had a podcast with Thomas Bywater from IECO. Now, IECO manufactures solar panels and for many years solar cells that went into other people's solar panels. Thomas is a solar engineer, electrical engineer, and he also happens to be a Sparky, an A-grade Sparky, and throw in the fact that he speaks fluent Mandarin. It was such an interesting conversation. We of course talked about his growing up in Brisbane, his university career at the University of New South Wales, and about the same time Martin Green, the famous Martin Green, was involved. Then we started talking in depth about some of the technologies of solar cells now and how they've progressed. We spent a bit of time on the ABC, all about contact, and also mentioned a little bit about agrivoltaics and a whole host more. It was quite a detailed, nitty-gritty kind of conversation, and the learning curve for me was very, very steep. And hopefully you'll get something out of this, because I certainly did. He's an incredible man, a true gentleman, and a massive brain. So without further ado, let's sit back, because I'm going to sit back, because I'm actually going to listen to this one, and let's get stuck into it. So I want to just start off with Mandarin. Let's just jump in there. You learnt Mandarin, and I got to ask you why Mandarin, and do you have a love of languages? Yeah.
Yeah. So in our high school, you mandatory had to do a language. So it was German or Mandarin, and Mandarin I thought maybe you could learn about the Great Wall or something a bit more interesting than the German. In hindsight, I would have loved German. I love Chinese too, but so that's why it was forced on us in a sense. And then after that, having got that base there, the school offered to go to China on a trip. So my family got behind that.
Wow.
So my mum was at the flea market, like selling curries and stuff to help fund that, because we didn't have heaps of money at that time. And it's quite funny to think about a rough as guts school, Caboolture, at that time.
Oh, this is Queensland, isn't it?
Yeah, Queensland, had that sort of forethought to teach Chinese. So that's why I'm doing Chinese, is because of that exposure.
What year are we talking about, Thomas?
So we're talking the late 90s. Yeah.
Okay, you show your age. That's late 90s,
Yeah,
so you're not that old. And so that is very progressive for it's very progressive for Queensland in general, isn't it?
It's your Joby Occupedison sort of
Wow.
location, right? But yet it had this sort of forethought. So, it is quite amazing. And unfortunately, I said to the school, hey, do you want me to come back and sort of pep the kids up a bit? And they're like, we don't do Chinese anymore.
Wow.
So I was like, oh, that's brutal.
It's funny you mentioned German, and you're an engineer, and speaking German is a very technical language, and it's actually fantastic for any engineering concepts, isn't it?
Yeah, and you're an old hand in Solar Valley, so you had the CARCO and the SMA under your hands. And so SMA was a fascination later in life, of course, and went to their factory and was amazing. I was like, oh, I wish I learned German as well, but you can't have it all, right?
You can't, and I think learning languages is fantastic for the mind. It's left side, right side. It's like playing piano. People who are multilingual or bilingual are a little bit smarter than people who can speak one language, and that's a fact. I love the idea that you've actually learnt a language that traditionally, from a Western point of view, it seems really, really hard. And is it as hard as what people think?
No, I don't think so. So the first thing I'd say is it's really hard to get mastery of a language.
Yep.
So I wouldn't say I've got mastery, but I've got fluency. So that means that when we talk, it doesn't sort of get all stilted or whatever. What people miss is that there is that sort of symbols in your day-to-day life. So you look at the percent sign and you don't say circle/circle. You know that it means percent.
Yes.
You know that's how you pronounce it. And the Chinese language is essentially like the @ sign, the $ sign, the percent sign. Like it's got meaning to that shape. So that once you adopt that and understand that you're already doing it and you can do it, and you know that it's not percent, like there's a specific way you're going to pronounce percent in Australian English, and $sign. You're not going to say $sign, you're going to say $sign.
Yes.
And so you've got all those tonalities already in your day-to-day life. So if you can bring that competency and that confidence to learning Chinese, I think you'll be fine. The difference between, let's say, learning German or Swedish, you need to invest in mastering the tones so you can reproduce them.
Right.
If you do that on the front end, and you go in there with that confidence, I think most people can learn it. It will take you a little bit longer than other languages.
It's interesting because obviously as human beings, we think in pictures. If I say 30%, if I say 30%, it's sort of you're conjuring up a like maybe a proportional pie chart or something in your mind's eye.
That's exactly what I was thinking.
It's that visual retention is obviously higher with visual images. If I say elephant, you don't see ELEPHANT, you see an elephant.
Yeah.
So Chinese is interesting because compared to say English or the Western languages, the structure of say an A or an H is nothing compared to those, for someone who doesn't know, those strange brush strokes that and there's quite a few of them. So you must have it's more visual, isn't it, than from that perspective?
Like a lot of things in life, you can remember them with stories. You can attach them to past memories, and so you have these building blocks in that language, and so you can essentially formulate the character from those building blocks. So you might associate, let's say it was a percent sign, you might make a story about circles, right?
Yes.
Which is, let's say whenever you see a circle, you say Robert, and whenever you see a slash, it's a hill. So you're like, Robert fell down the hill and Robert was at the bottom of the hill. Like there's ways you can sort of structure a story to remember that pattern.
Yes.
I'm probably not explaining it very well, but essentially you don't have to just rote learn things. You can use other methods to take advantage of your existing memories. So that's really interesting, just finding ways to do it smarter and not harder. Like with engineering, like with our work every day as electricians and as installers, we're trying to work smarter, not harder, use lifting aids, use scanners on our phone instead of handheld scanners, all sorts of things to make our life easier. It's exactly like that with languages.
That's I've never heard anyone actually say that, but it makes perfect sense. So obviously, you did languages in Caboolture High in Queensland. When did you decide that you wanted to become an engineer? And I ask that because a lot of people know when they're 10. Other people, they're 60. They still don't know what they really want to do. What was your story in that respect?
Yeah, so I've always had a fascination with solar. We grew up watching the Beyond 2000 programs.
I remember that.
So I always had this idea I'm going to have like a solar-powered bicycle or car or something. And I think people like Dick Smith are really influential at that era, that sort of late 80s, racing across the Nullarbor with a solar-powered car. So it was really top of mind. I then went to China after university, which was in business. And in China, it was very apparent that renewables were coming in a strong way. So I thought, we better get in front of this at UNSW. So that's why I did that engineering. And UNSW is a great resource for our country. Like imagine having a world-leading, if it was biotech or AI university in the country. Like that's the kind of power that we have in Australia.
Was this Martin Green?
Yeah, Martin Green.
Wow.
Look, Martin Green's fantastic, but for the actual student cohort, people like Stuart Wenham, people like Alistair Sproul were more probably involved in the actual students, and Jeff Stapleton that you would know.
Yes.
And so those three people sort of really influential in moulding a lot of the capacity we have in Australia, which is why we've got probably, I would argue, the most capable group of people in terms of executing projects. We don't have manufacturing here, but executing projects, we've got an amazing cohort of people in this country.
And you specialise at the end. When do you start with an engineering degree at University of New South Wales? When do you start?
So we actually started from the beginning.
Oh, wow.
So I do know that there's some universities that have, let's say, a common first year of engineering. Yeah. And to some extent, even though you're specialising, that's the reality, right? You're doing the first year maths, you're doing first year physics. So we sort of had that same thing. But all the way along, we knew that we had this pathway ahead of us, and great group of people, like people in renewables. I'm sure there's other industries too, but I think if you were to study something cutthroat like maybe law, you wouldn't have that collegial environment that you do have in renewable energy schools at places like UNSW and Murdoch.
Interesting. Do you think engineers are born? Is it nature or nurture?
No, I think engineering essentially is problem solving, right, at the lowest possible cost.
Yes.
So I think all humans are constantly solving problems in their life. So I think it's just a matter of directing that energy that people already have to something that they're passionate about. But
surely some people have got more a greater propensity to analyse, to see pattern recognition. It's all about patterns, isn't it? And being able to recognise what's actually going on and then taking those leaps to something else.
Yeah, 100%.
There must be better people who are better than others.
If I look at the cohort of our group in UNSW, right, I would describe myself as not a natural engineer in terms of I wouldn't be able to come up with ballistics and calculus if it wasn't already there, right?
Right.
Having said that, the people who were really capable academically tended to go into that research path. The people who were sort of like your B student started businesses and have had an impact on people's lives.
Can you repeat that again? The B students basically went into business. I'm teasing. No, that makes sense. I mean, we all have to know our limitations and find what we're good at. Now, you specialised in solar cells. Can you give us a rundown specifically what you were studying in regards to the solar cells in that degree?
Yeah, so we did learn how to make panels.
Wow.
Make cells. So I would break it down into, there's two stages, right? There's the assembly of the module.
Mm-hmm.
There's the creation of the cells. So those are two sort of separate areas. It doesn't seem like modules are complicated, but actually they are. And that's why you've got some of the heavyweights in the industry that have actually been module companies, not cell companies historically. Because there is something to know about making panels. And so we basically were looking at how do you make a good cell? So that's tweaking your processes with your chemical vapor deposition to achieve different things with the wafer. And then with the modules, it's about how do you arrange those cells electrically so they give a great outcome, they're not too big, they don't break when the pressure is applied from the wind, that sort of thing. So that's essentially what we studied. Unfortunately, BP Solar was the only factory in Australia by the time we graduated.
Yes.
And very soon after that, they did shut. And we could see the writing on the wall in those last couple of years. So that means that a lot of people have gone outside of manufacturing from that group of kids and went into integration in the C&I space or in the residential space.
You mentioned BP. My first job was Queen Vic Market.
Oh, yeah. I remember that project.
Yeah, they were BP laminate panels, really heavy handling. We were handling them with glaziers suction cups. There was about 1,300 of them. We broke 3, but they were broken when we opened the box.
Wow, that's good going.
Yeah, it was, and they were so heavy. To actually join them together, for want of a better expression, 4 of them came together with a spider clamp in the middle, and it was a horrendous job. But yes, they were really heavy panels, and they were very expensive. They were around about $10 a watt, compared to the prices now, which it's phenomenal. So you're starting off with these BP solar panels, and that was really the only thing that was around at the time for you.
Yeah, that's right. And jobs like Queen Victoria actually did go on to inspire people, right? So there were a few jobs like that. Sydney Olympics.
Yeah, right.
So I was exposed to some of the work on that, and that was really influential. And later at Suntech, we worked on some of the things for the Beijing Olympic Games.
Oh, so you were at Suntech?
I interned there with a person called Alice Lang, and there was other people, of course. So we interned over there, and that was one of the things that we were looking at is how do we use the MSK technology, which is like a thin film type of technology, as well as the crystalline ones to do BIPV for the Olympics. Okay,
so for the people who are listening, can we just go explain one of the acronyms, the last one, BIPV?
That's building integrated photovoltaics. So at the Sydney Olympics, a lot of the houses in the Newington village there, they actually integrated the panels into the roof of the houses. So that meant that all the athletes, all the media and all that came through the Olympics, they got exposed to solar, so that was fantastic. And the same thing again in Beijing, they were trying not to have solar be obtrusive. They wanted it to be something that flowed naturally with the environment. So they were including the solar generation into the building structure, so it was unified and the aesthetics were pretty appealing.
Because that's what people have to remember, that when a building is constructed, and especially in the last 5 or 6 years, where they're designing these large buildings with tiny tolerances, they weren't designed for solar to go on top.
Yeah.
So the structural engineer comes along and he's trying to try to do his calculations of what this roof can actually hold. Is that something that you experienced a bit with in your day-to-day life? Are you interacting with structural engineers and doing that kind of thing?
Yeah, I think that's another area where we're really strong in Australia. We've got great companies like Gamcorp and that are looking at these things really in a detailed way. It's a day-to-day thing that we're considering structural concerns. So whether that be the deformation of the building, the total weight that it can hold, catastrophic failure of structures. Yes. It's really important, and that sort of engineering flows into the electrical work, if that makes sense. So when you come to a building, you're thinking about how much watts can I put on there as an electrician, right?
Yes.
But you're also thinking about, as an engineer, if I load up the west too much, what's going to happen to the east? Is there going to be some instability of that structure?
Well, we will talk about vertical integration of solar panels.
Yes, I believe
in 20 minutes. We'll talk about that. We'll talk about that, and also potentially vertical integration onto commercial buildings that have been maxed out from a panel perspective, and the structural engineering. You're pushing it. We'll talk about that. We'll talk about a lot of stuff. So IECO, and I pronounced that correctly because I remembered your memory trick. They were making cells for other panel manufacturers, weren't they?
Yes, that's right.
Yeah.
So long time ago, they were doing aluminium. So 20 years back, they were doing the aluminium. The founder of the company, who's a doctor, Dr. Gung Chen, so his surname is Chen. He's the CEO, and he was exposed to the aluminium side of the solar industry, and then he saw the cells coming. So 16 years ago, they started making those cells. And so they were there from pretty much the start of the mass market side of the industry. Right.
Now, can you explain, and look, a lot of people listening are in the renewable energy field, but some aren't. Hopefully more who aren't are listening to these podcasts. So as the three main kinds of cells that are readily available are mono, poly, and amorphous. So can you explain the differences between those three?
Yeah, so the difference between the cells is essentially in how the materials come about. Amorphous is pretty much gone by the wayside, but if we look at mono, it's a very tight crystalline structure.
Right.
So that has the advantage of there is not so much possibility to lose electrons that have been bumped by the sun's light. Mm-hmm. So if we go back to how a solar cell works, what is it? It's a piece of semiconductor that photons come from the sun into the front side of that, and they dislodge electrons and cause them to move along in a circuit, right? Now, when you dislodge those electrons, maybe they'll want to go back into the hole where they came from.
Right.
Rather than be collected for your energy purposes. So the mono is a very tight crystal structure that allows that to happen easier. The amorphous, you can think of it as being super messy structure.
Right.
So the electrons get bumped out, but they might go back where they were. Okay. So you might need a bigger surface area of that material. So that kind of stuff is really great for calculators, right? So even today on your calculator, amorphous.
Oh, they're all amorphous.
Yeah. If you go to the solar panels that are on your house, almost for sure they're mono. And in between those two technologies is poly.
Because poly used to be really popular.
Yeah, because it was less energy to produce it. So essentially what we did is we melted the silicon, we just poured it into a big square mold and cut that up. Essentially that's poly, like simplifying a lot of steps here, but that's essentially the case.
And mono is an ingot that you grow and then you slice.
Yeah, so we draw that out slowly from, so we heat all the silicon up, and we have a seed crystal that sets the structure. So I don't know if you, as a kid, ever did science experiments with Condi's crystals. Some kids have done that, where they've drawn out a crystal, kind of like a thunder egg sort of style crystal from a solution. But essentially what you're talking about is little diamond shapes are forming. If you start with a small perfect diamond shape at the top, you'll create a lattice of all these crystals. And
so you're an alchemist. You're alchemists, basically.
We are alchemists. We are making gold from lead, that's right.
Wow.
No, but anyway, the basic upshot for a homeowner is that we can use a lot less space using the mono. The amorphous is maybe cheaper to make in some sense, but takes a lot of space, is not practical for a house.
But at the end of the day, if I've got a 400 watt, let's be up to date. Let's say I've got a 500 watt panel or 450, 470, and it's a poly, and I've got the same wattage in a mono. The mono is going to take up less room, so overall per square metre it's more efficient, but at the end of the day they both produce at their peak whatever their rating is. That's
right. So we talk about that being the nameplate of the panel. So back in the day there was another qualification which was plus minus.
Yes.
So if we go back to the BP days, when they produced the solar cells, when they came off the production line, there was some inconsistency in the output of those cells. So they would actually produce, let's say, panels that had a rating of 60 watts, but the next day that same production line might make 70 watts. So they would badge everything 65, and some would be under and some would be over.
Plus minus.
Yeah.
Okay. But nowadays, is that tending to...
Nowadays, we don't have to do that. So the manufacturers like IECO and I think Trina and others, they only badge it below what the test is. So that's to say you always get what you pay for. But there are some people that still do use that plus minus. But all I'm trying to say is that back in time, it wasn't so easy to say that all performed the same because some of them had bigger tolerances with respect to how consistent their output was.
Okay, so is it a case that, say, the range of panels... So give us an example of an IECO range between... a couple of panels between, say, 450 and whatever, 550. Give us a couple of example model sizes, and then I'll ask the next question.
Oh, okay. So, I mean, the classic example from the IECO range is that 2 square metre panel that's 475 watts.
Right.
That's your classic panel.
Right. And the next size up is?
Is your 510.
Does that have the same physical...
It's bigger physically.
Oh, okay. So, because I was under the impression, and you got to correct me if I'm wrong, that when it came to grading of the cells after production, it's like, there's a 450, there's a 470, there's a 450, there's a 470.
That's still happening, of course.
It does, yeah. Right. Okay, so the same, and the cell is the same physical size.
Yes.
Okay, so what makes that a 470 and that a 450?
Yes, you've got very tiny differences in the impurities in the wafer, I guess you might say. Really, it comes back to the wafer. There's so many stages in the manufacturing that a tiny bit of variance in the amount of metal, boron, phosphorus, or whatever that's deposited will have this tiny impact on the output. And 2 or 3 things combined might add up to 5 watts difference. So when I say 475, we also do that panel as a 470, so that's mentioned here.
Okay, right.
Yeah, so we would offer them to the market badged appropriately. So if they're 471, we'll badge them as 470. If they're 476, we'll badge them as 475. So we generally offer a lower price for the smaller output.
Yeah, gotcha. It's a really interesting area because obviously the panels are getting bigger.
Yes.
And you talk to the structural engineers, and I had a conversation with someone from GamCorp just before you came in.
Right, yeah.
And they go, we don't want these big panels on the roof, right? They want to go back to a smaller panel for various reasons. But the panels are getting bigger. Do you think when it comes to a roof mount scenario, and I won't talk about ground mount because I think that's a special case, is there an upper limit where it physically becomes too hard to handle from a cost-benefit relationship where you go, and I'm talking about install cost, material cost ratios, that the panel becomes way too big?
Yeah, well, the first thing to say is there's probably always going to be a 2 square metre panel on the market because Europe and Japan have these requirements around the size of modules for residential jobs. So that size will always be there.
Yep.
Where you'll see variability is in that CNI panel that's sort of about 2+ metres long.
Right.
That's sort of being dictated by that 25 kilo weight. There are some markets that sort of look for that weight. That dictates to some extent the size of the panel. The dominant thing that dictates the size of a panel is the container dimensions. So because most solar panels are shipped in a shipping container, so we want to figure out how do we pack the most watts into
this is a mathematics question, isn't it?
And we've already solved that question.
Wow.
The panel needs to be 2382 by 1134.
Can you repeat that? Can you say the dimensions again?
Yeah, so the absolute maximum watts in a container is a panel that has the dimensions 2382 by 1134.
Yeah, wow.
So that 1134, which is 1.1 metres, right? You stack those two on top of each other. That's the height from the floor of the container to the ceiling, including some pallet spacing.
Yeah.
Pallets.
That's really interesting because obviously, panels are so cheap now.
Yeah.
They really are, and I find it must be hard to make money when you're talking about cents on the watt compared to what they used to be. It seems it's really, really hard. So it's really interesting to see that not only that is taken into consideration, but it's how the panels can be packed, how many can we get in a container. We know shipping containers are not going to change in size, are they? We know that's not likely. So this has all been carefully worked out. So who are you allowed to say who IECO were making cells for? Is that Or is that...
I would just say, look, it's the biggest exporter of cells historically in China.
Right.
The biggest cell maker is another company at the moment, but they have made for most of the major names in the industry, and particularly the major names overseas where you have a solar panel factory, but they don't have the cell capacity.
Okay, and so you're sort of not allowed to say who they are? No.
I just don't want to take some of their
glory, I understand, totally. So when did IECO decide to go, hang on a sec, we're going to make our own? When did that happen?
Yeah, so it happened back in 2016. So in 2016 was their first patents on their two-step back contact process.
Yeah, I want to talk about that. Yeah.
So IECO has been participating for a long time in choosing how big the cells are going to be. So working with the wafer companies to figure out what's going to be the dominant style of cell at a particular point in time, whether it's the PERC era or the TopCon era and now the back contact era. So that's where that's come from. They've had that dialogue. They've seen that their position in the market has been eroded by, let's say, the price points in the module business. So if you look down the module chain, a lot of them don't make any money. On the other hand, they're not really innovating in the way that we would like. So we thought, well, we can bring some innovation. We can help our distributors and our installers to differentiate, so they can capture a little bit of that margin whilst giving a benefit to the homeowner. So they'll be a sustainable business because they're profitable, but also the customer will get a better outcome. It's going to look better and it's going to work better. So everyone wins. So that's what they were really aiming for. Our CEO, he's really clear on the upper limit of silicon and chasing it down. So I think when a lot of people go to work, let's say you work in the tyre shop, okay, you don't exactly know what you're doing for changing the world. Our CEO is really clear. The upper limit is 29.56 for the efficiency of a single junction solar cell. We're going for it. That's our goal. Every day we wake up, we're going for that. So that drove his decision to go for that, because he saw other people looking at the commodification of solar, looking only at, let's say, how do we make it for the cheapest cost, and he wanted to do something different that drove the industry forward. So I think that's really encouraging. Like every day we get up, we know what we're doing. We're heading to that 29.56 efficiency. And why are we doing that? Because it can make solar more functional. Because it's one thing to be cheap, right? But if it's massive, you can't fit it on things. You need it to be as small as possible if you're going to charge batteries on the McDonald's shop or on the car dealers or wherever you're going to go. So efficiency is so key to the next stage of solar, which we call Solar 3.0, which is where you're integrating storage at the building level with coordination of your appliances.
It's interesting because at this point in time, solar's so cheap. Some people are starting to talk about it as being looked upon as being a building product.
Yeah.
Because you start thinking of fencing, you start thinking of, hang on a sec, it's cost me this and this to make it out of this. I can make it out of that. And by the way, it actually produces energy as well. Is that something that IECO... So, is that something that IECO are looking into, or is that something you can talk about?
Yeah, I think if we look to the European context, you're already seeing three developments in that space. The first one is solar balcony systems. If you look at how they're set up, they're essentially vertically placed, right? So they're hanging off the balcony, much like how BIPV might be set on a building, like in the curtain wall. So they're vertical. There's also a lot of fencing. And the other innovation is roadside barriers. So that can be for like noise prevention. So that is really interesting. Having said that, I think those are niche applications in the main, right?
At this point in time, I think you're right there. Now, you mentioned about back contact, and you mentioned also PERC, and there's a third one that you mentioned.
TopCon.
Can you explain the chronological order of them and what it actually means from a output perspective and a degradation perspective as well?
Yeah, so IECO was really influential at the sort of start of the 2010s in working to commercialise PERC. So PERC was a technology developed by UNSW to make solar cells work better. And at that time, it offered us some benefits that weren't present in the poly panels that were dominant prior to that. It also helped to improve the efficiency such that even though you needed more energy to make mono, because they were so much more efficient, it overcame that hurdle, and that's why we stopped doing poly panels. Poly before, if you remember, was the crucible. We just melted the silicon, let it set. The mono, we draw it out slowly with that seed crystal. Now, PERC we reached the limits of that in probably the 2019, 2020, that sort of time. We could see that it wasn't getting better.
Right.
And we went to that N-type TopCon.
Right.
So N-type changes the actual structure of the semiconductor. So before it was a P-type material. So the P region of the semiconductor was the dominant area, and now we've gone to the N-type. So why did we have P-type? Well, it's a funny story. It worked better on spacecraft. So that's why P-type was sort of dominant.
Right.
Over time, we came to realise we're not putting that many panels on spacecraft. Let's go back to N-type that's actually more efficient. And we used the TopCon method. And now we've gone to back contact. And what that's done is take the metal off the front side of the panel. So there's no metal on the front side of this cell, as you can see. And we put the positive and negative contacts onto the back, so that more light can come into the panel.
Now you mentioned about spaceships and satellites, and there's a lot of satellites up there. A lot of them, contrary to what people believe, can attach to giant helium balloons. But that's a conversation for another time.
Oh, right, okay.
And they do have actual solar cells. Now I was under the impression that there's some incredibly radically efficient solar cells that are just for space, because I remember 30-40%. So this is different kind of solar cell, isn't it?
Yeah, so if we look at some of those Spectralab or Boeing solar cells that are really crazy efficient, they tend to be based on gallium.
Gallium arsenide, yes.
There's different materials than what we're typically using on the terrestrial panels.
Right. I like that.
But that thinking around what structure do we want in the semiconductor had been sort of set some time back,
right,
before even those cells were available. So if we look at what cells were going on to space stations in the 80s and 90s, then you probably find that they were P-type poly panels, mostly. Obviously, specific spacecrafts, your mileage may vary, right? But in general, that's true.
I like that.
And so that was dictating the structure of the semiconductor. We flipped that back to N-type as an industry. And that was a great advancement, but we did find there was some drawbacks with the TopCon, particularly if there was some moisture ingress on the rear side. Some of the packages, some of the cell constructions, together with the EVA or whatever that's going around them, were seeing some degradation, and we've been able to overcome that by either the HJT or the back contact technologies. That
HJT, heterogeneous...
Yeah.
Yeah, please finish it off for me.
Tandem junction, yeah. No, it's that technology we think has a lot of advantages, but overall we still think the pathway will be BC, and that's why most of the new production that's coming on stream for cells and modules is a type of back contact. Okay, so this 29% you mentioned, is this like I've got a vineyard. Well, I got 20 vines. I'm trying to grow some Merlot, and I'm going to be making some wine when they actually produce some grapes one day. Because I like red wine. And I know that no matter how much I ferment that wine, I'm not going to go past 18 or 19% unless I start making whiskey, and it's a distillation process. What tempers, why is it 29%? What stops it from being a higher percentage using silicon? Yeah, so we can understand just from physics, like if everything was perfect, what would be possible? So it's not that we can't make cells more efficient than 29. We absolutely can. Oh, okay. Using something like perovskite, multi-junction cells. So they're just more complex manufacturing scenarios. So we're just talking about the basic single junction PN structure. Right. That's the maximum that it can produce as we understand it now. That limit has actually been adjusted. So when I was a little boy, it was a lower figure than 29.56. But over time, we've come to understand more about physics and how the materials work, and that's how we've got that figure. And it's just a question of how do we get things off the front surface that are stopping the light coming in, and obviously we've already solved that with back contact. Right. And then how do we then make sure that those electron hole pairs, I mentioned before, the photons bump the electrons into a sort of a circuit, a flow of electrons. Right. How do we make sure that all of that gets captured and doesn't recombine and just stay where it is? So that's sort of the challenge of solar, is get metal off the front, make sure the electrons that are bumped out by the photons keep flowing and make a circuit. So when the sun is shining down on a solar panel, and obviously maximum output is when the rays are perpendicular to the surface. Yes. Now, the sun changes spectrally
even during the day, let alone through seasons. Is there certain colours or ranges of colours that are more efficient at the panels producing energy than others?
Yeah, I mean, obviously the black that we see on solar cells, that is a function of it not reflecting the visible spectrum.
Right.
But you've touched on why you do have perhaps multiple junctions in a solar cell, which is to capture other types and colours of light.
Right.
So there are even cells now that are designed to capture light at night time. Different spectrum, right?
Wow.
So potentially if there's heat there, we can think of that as being a form of infrared energy.
Well,
right?
it's a frequency.
It's a kind of light in a sense.
Yeah.
It's a bit hard to wrap your head around, but there can be scenarios where you can capture that even though there's no visible light. And if
I'll re-ask the question. Not light spectrum, different frequencies of light, because it's all frequencies.
Yeah, that's right. So that's sort of the challenge with those multi-junction technologies is you will have materials that capture different frequencies of light.
Yeah, wow.
And that brings complexity to manufacturing. There's two reasons why we don't do it. First is hard. Second, are we confident it's going to be stable and reliable?
Right.
So the solar cells that you're using now, in essence, that single junction technology has been on the market since the 70s, right? In essence. Obviously, we've improved it in how it's structured. If we want to then start introducing a lot of different materials that haven't been used, maybe we can't get those materials in mass scale.
Yep. Or
maybe by having those materials next to each other, they're not stable and there's some kind of mechanism that causes them to degrade. So that's a beautiful thing about silicon that we have now is it's so well understood. How does the silicon work with the glass? How does it work with EVA? How does it work when it's got boron or phosphorus or whatever? We all understand these things. So I think that's why we haven't made that leap to multiple junction technologies doing the different frequencies of light that you mentioned.
Yeah, look, again, there's a commercial reality that tempers all our decision-making process in this world, and obviously marginal diminishing returns and all of the things that you mentioned, availability and reliability of the raw materials. I mean, you might be able to make a solar cell out of a diamond, but you're not going to do that because diamonds are expensive. Now, the whole bifacial panel scenario, can you explain to our listeners what that actually means? We're still talking about, say, a 470 or a 475 watt panel. What is the difference between a panel that's not bifacial compared to a bifacial in regards to overall output?
So the first thing I'd mention is that a bifacial panel needs glass on both sides or some kind of clear material on both sides.
Right.
That typically impacts the weight. So we make both types of panels at IECO. Bifacial, which can have light on the front and back side.
Right.
And monofacial, which just takes light from the front side.
Right.
Sometimes the cells that are in these packages have the capability, but they've been blocked on the back side by some material, right? So if we want to keep the weight down, we use single glass, which is going to normally mean it's monofacial. The light's only coming in from the front. But going back to what the difference is, normally we optimize for front side production.
Right.
So if I have a bifacial panel, which means the light's coming from both sides, it's not the case that I get the same generation from the back as the front.
Of course not.
So normally we'll have a bifaciality factor, which will describe the proportion of the output from the rear side to the front. And that might be something like 80%. But then you've got to consider, where's that light coming from? Is it coming from a white reflector?
Right.
Or is it coming from black bitumen? It's going to have a different albedo.
Or grass if it's... And does that change too when take into consideration that 95% of the solar farms in production now and for the last couple of years are using passive tracking east-west configurations? Does that play a role with the suitability of a bifacial panel in that respect?
Yeah, I think that's really interesting is the trackers, as they've become easier to install,
they've
become a lot cheaper too. So panels have got cheaper, but so have the trackers. Trackers have also had a subtle improvement, which is their reliability has got a lot better. So whereas before you might make some assumptions in your financial model that it's going to be offline for X, Y, Z reason, now you might say, well, the amount of time it'll be offline will be much less. So that's another benefit that we've got. So they got cheaper just from a footprint and install perspective. They've also got cheaper because the panels are more efficient. So whereas before you might have had, let's say, $1 a tracker per watt, as an example, right? This is just a theoretical. Now, because you got more watts on the tracker, its effective cost is, even though the metal might cost the same amount, it's having a bigger impact. So that's been really helpful. But going to the bifacial, when you've got that tracker chasing the sun, to some extent, there's not as much need for bifacial in a tracker.
That's what I thought, yeah.
Where you would potentially see a bigger benefit is in a static array where you've got it tilted on a rooftop and maybe the roof is white or something.
Yep.
You'll see a really big change in the output because of that.
Yeah, that's what I've wondered too. When the majority of commercial solar roofs are installed panel-wise FTR, flat to the roof, right?
Yes.
You know, you're talking about 5 or 7 degree pitch roof, and in most cases the roof material is a lightish colour. I always thought, well, how much benefit are you getting from a bifacial when it's like that, and the roof's not that good, and plus heat plays a role as well. You know where I'm going, Thomas. Yeah. What's your view? My personal view, yeah.
It is relevant. So we've got a test site in Parramatta, and we're seeing that the bifaciality on a flush to roof installation still delivers you single-digit percentage benefits.
Okay.
So it could deliver you 3 or 4%. Now, maybe it doesn't cost that much more to put on, provided there's no impact on reliability. So one of the concerns we might have as an industry is if the shading's uneven on the rear side, do we create hotspots in cells where they've got, let's say, a rail there or a cable or something that effectively shades it?
That's a really interesting point.
And so far, we haven't seen that play out. So far, there's not been reliability concerns for that. So we think it's good. In general, bifacial has benefits. And that's actually a myth about back contact, is that you can't do bifacial with it.
Right.
Now, we actually do different types of cells for bifacial to monofacial.
Right.
But absolutely you can do bifacial.
Wow.
And that has been one of the, I guess, advantages of going to the TopCon N-type based bifacial that IECO have,
right,
compared with some of the older P-type back contacts where they did have a challenge doing bifacial. So we think bifacial is really relevant on those tilt jobs, particularly. Let's say you had a vineyard.
Tilt. Yes. Yeah.
Let's say you had a vineyard, 30 Merlot plants there. Then you might have a ground mount array,
right?
And we think you'll benefit from that.
That makes sense.
Yeah.
That makes sense to me. Yeah, totally. Especially, well, they're saying the what was that reflectivity index you mentioned?
Talking about the albedo.
Yeah, albedo. Yeah. So I've heard that green grass is much higher than what people think.
Yeah.
Plus the fact that you've got a living organic material that's actually creating a microclimate underneath anyway. So which obviously, because strangely for people who don't realise this, electricity doesn't like heat, does it? That's the weird thing. Oh, it's 40 degrees. They're going to be producing more. No, then you're going to be producing more on that cold, clear day at 21, 22 degrees when the sun's pumping. The whole panel area is really interesting. It's funny for me though that it hasn't progressed efficiency-wise compared to, say, battery storage energy density. But maybe that's comparing apples to oranges. I don't know, because, batteries, they've come down massively in price in a really short amount of time. But I suppose they're two different things.
Well, I mean, when I was first exposed to solar, I think it was $4 a watt. And now to see it at 40 cents a watt, I see that as a massive change for the homeowner.
I wasn't saying more the price, I was saying more the efficiency of the panels.
But I mean, if we think about those panels, a typical solar panel, one of the earlier panels that I installed was BP 60 watt. And now the panel, if I was going to pick up a panel and put on my grandma's house or something, that's going to be a 475, maybe a 480. That's nearly 10 times bigger. I mean, it's not exactly 10 times, but it's massively bigger in output. Now, granted, the physical size is a little bit different, but that's a massive step forward. And we actually have been thinking about the problem you're mentioning. So how do you actually make the module better? So in our third generation, we've actually taken some of the final areas off the panel that don't generate, and we've moved them to the back. So we've got the cells right. We've already moved that metal from the cell to the rear side.
Right.
But still on the panels, you have these kind of like junction areas, which we call buses, that are occupying generation space and they don't make any energy. So we've put them on the rear side in that third gen panel. And there's other people thinking about similar things, like how to get more out of the cells.
Mm-hmm.
We've already made great cells. Let's make great modules.
Yeah, I understand.
And there's other ways we can do that. For example, we can potentially have the inverter talk to the panels electronically and understand what they're doing. So at the moment, what you have is...
What, cell monitoring?
Yeah, basically cell monitoring as opposed to optimizing the cell.
Yeah,
Just let the inverter know really in a detailed way what each panel's doing.
Wow.
And it can potentially improve that MPPT experience.
Wow.
We can go and maintain, as soon as there's a problem, these kind of things. So I think you'll see some amazing technology across the next 5 years that improve the output of panels.
The going back to the bifacials, it's a funny one because we talked about that. You said they've got an extra bit of glass in them, so they're going to be bloody heavier, aren't they? And then you're coming into that whole roof structural engineering kind of scenario. And we won't even talk about hail loading because that's a sore point with structural engineers. If they try to incorporate that into their calculations, they're accused of being more conservative than they already are. But it's an interesting thing because the way I see it, like obviously the price of the panels and the price of the framing, the racking, etc. It's a fixed cost, and then from a financial perspective, if I'm putting on this panel, it's more efficient, it's going to produce more energy in the long run, and we all know commercial solar is about MPV, IRR, and all those other financial metrics. What's happened with the IECO panels in regards to the panel degradation, which has really improved a lot in the last few years with most panels? Is that something that you guys are concentrating on?
Yeah, so the degradation annually is marginally better than TopCon's. Typical TopCon's about 0.4 per year, something like that. We're at 0.35.
Right.
I don't think that's a material factor for most people now. Like, it's so small that it's not that big of a consideration. The thermal coefficient is a bit better.
Right.
So we think that's probably going to have more impact potentially in mining projects. So Australia, a lot of the big projects now are going in that sort of West Australia, that sort of Pilbara space, if you like. And that's where it's really hot. And so having that thermal advantage helps us by having that 0.26 instead of 0.29 as that coefficient.
That's very interesting.
Yeah, and I think that most people, if we want to look out 20 years, they potentially will adopt another technology in that third decade. That's our prediction. So if we look at what's happening now in Australia, the systems that have been put on in those early 2000s are now being refreshed in some way. They're just too far behind what's possible now.
Yep.
So they'll have to be recycled, and that's another area that we think having our setup will just make it a bit simpler for recycling. If you just have copper, silicon, as opposed to aluminium, silver, lots of different metals.
Yep.
So we think there's potentially an advantage on the recycling front. We'd love to see that looked at more strongly by government, actually.
Yeah, me too. I think a lot of us, I try to remind people in this industry on a pretty regular basis from a personal perspective. I'll take my Greenwood hat off. No, Greenwood also agree, but I'll probably talk a bit more personal here that we are in this space where we should be leading by example in regards to best practices and sustainability, and treading lightly as we can. No one wants to talk about reducing energy consumption, but that's a conversation for another time. Now, you mentioned about the mines. There must be a real issue with soiling of the panels on the mines. Because they're dusty environments, and we know that how much that reduces production. So when they go into a mine situation, is there advice that you give the asset owner? Bloody clean these panels.
Yeah. So the EPCs we have in Australia, like Greenwood and others, are very competent, and we do see pretty detailed maintenance schedules. We see mowers being specified. Okay, you're going to have potentially grass or something growing up and specifying frequency of mowing. And then there's robotic cleaning as well. So when I talk about mining, I mean the very large sites.
Yes.
So they do think about these issues, and they're using either compressed air or some kind of solution to robotically clean those modules on some kind of timetable. So that's how they deal with that. On our side, we do have some tolerance for shade within our panel.
Right.
So we have the ability to do some partial shade bypassing where that becomes an issue with bird poo, for example.
Yep.
During the time between cleans, we do have some stability there that wasn't there before in your poly panels and your panels going back, those BPs and that sort of thing.
Yep.
So that's very exciting. So it's a bit like the degradation. We've improved the temperature coefficient, we've improved the performance when it's dirty. Having said that, a lot of the debris in those areas, it's like a film. So
Yep.
it's very even across that.
Right.
We don't have an advantage when it's an even shade compared to other panels.
Yeah.
But we do have it if it's patchy or there's some bird poo or something like
Which
that.
is the reality that it's going to be in most situations.
Yeah.
Look, back to the degradation, I did some analysis about a year ago, a whole range of panels, and honestly, over a 25-year period, if you're looking just at degradation and all other things being equal, it's, can I use the term, bugger all difference, really. So I think the temperature coefficient and the panel's ability to cope with warmer temperature, that's a big thing that should be pushed. Panel degradation, they're all pretty similar, and even the ones that are slightly off, it's not that much difference, even on a 1 megawatt, 2 megawatt array. Now, the frames, I've noticed the frames, they're getting so thin, and like, I remember when they used to be really thick. I remember, I'll say, Kyocera Japanese panels, they used to have a rail in the middle. And how have you overcome, how have you maintained structural integrity with the frame, but still reducing the overall weight? How do you do that?
So the lightweight panels that we have, they still do have those
we'll
struts
talk about
on the back.
Yeah, wow.
So we haven't totally done away with those mid struts. But if we look at the types of loads that panels experience in the main, there's a lot of uplift that we're talking about. Those struts used to not really contribute to that unless they had an adhesive to them. So from that point of view, the struts didn't contribute to the main structural stress.
Right.
If we look at why we've got frames on the panels now, it's not so much for the strength of the module as opposed to preventing cracks propagating. So what happened maybe about 6-7 years ago, there was quite a lot of frameless laminates in the market, and those frameless laminates, when they're installed, what would happen is people would bump the edge of the glass. And I don't know if you've ever cut a sheet of glass, but you kind of like score it with a knife.
You do.
And then later you put it under stress and it snaps along that little line. And it's almost unbelievable that little defect can snap in that straight way.
Absolutely.
But that's what would happen, is that people would bang it on the tray of the ute, or they would bang it on the ladder, or whatever they would do. Put it on there day one, there's no problem. Come back 2-3 weeks later, the cracks propagated across. So to some extent, the frames function on a double glass panel when it's 2+2 glass is to protect that edge from coming under stress.
Right.
Yeah.
I didn't realise that.
So
yeah.
I mean, it depends on the size of the panel as to what the role of the frame. But if we want to talk about this 2 square metre panels,
yes,
to some extent, if I was to give you the appropriate clamps and a glass laminate, it could be installed without that frame, provided you didn't bump it on stuff.
Wow.
So that's why I think the frames, we've been able to take some steps back, is we understand structurally the glass by itself is actually pretty resilient, and in some cases having the frame there actually introduces complications to how the stress plays out on the glass and can cause damage. But having said all of that, we still believe you should use a framed module.
I agree.
We're not suggesting use a frameless module, but that's why the frames have gone a bit thinner and that sort of thing.
Right.
The other thing is the bifacial aspect. So if we go back to what you were talking about, the light coming in the rear side, what we actually discovered in the industry as a whole is that the short side frames, so that's the bottom and the top frames, they could potentially actually shade that rear bifacial part. So we took away the lip on the top and the bottom to improve the output with respect to the bifacial.
That's really interesting. Now, how important is the actual installation of the panel? Like, we've all seen mid clamps, end clamps, people with the rattle guns, and there is ways of mitigating rattle guns, but we won't go into that detail. But surely you've come across and you've gone, hang on a sec, we got microfractures in that panel because that guy's it's 70 newton meters. It should be 12 or 14. So is that something that you push hard to the, so you IECO, you wholesale the panel to wholesalers. So is that something that you push, or is it well known now? Don't go hard on the end clamps and the mid clamps, because you will create these.
Most of the guys in the industry know the exact ugger-duggers to put on to create 20 newton meters of torque. Yeah. We don't see that as a big problem.
Right.
Where the problem comes in reliability of a system as a whole, right, is normally around something to do with the cable reticulation. or to do with the terminations of something like a junction box or a switch gear or something
Absolutely.
like that. So if you look at any system that stops working, your number one target is going to be moisture ingress to the wiring harness at some point, be that
True.
where the BPs are in the junction box.
Yep.
I love to fill them with gel. Not everyone agrees, but they do get wet, just saying. And then the other thing is around the connectors and how they've been tightened,
Yep.
terminated. Sometimes the connectors haven't been properly pushed together, hasn't formed a great seal, moisture gets in there. Sometimes the connectors aren't held onto the rails properly, so they're dropping onto the roof, they're getting wet. So that's what we typically see. And if you go even onto your LinkedIn, onto your crap solars or whatever, and someone says, oh, this job stopped working, very rarely are they going to say, hey, here's a photo of this clamp that was over-tightened.
Yeah, no, you're right.
It's going to be, hey, look at this corroded connector. Look at this melted
Correct.
Copycat connector. You know, look at where this cable has been rubbed against some kind of sharp metal surface, like a cable tie or an edge of a cable tray.
I think it's also important to remember that maintaining correct bending radiuses with all cables. We're talking about multi-strand. You start bending the bastards past that certain point, and these things break down, and their ability to transfer energy is reduced. It's not rocket science, but we've seen, like we used to do a lot of audits, and we've seen some horrendous stuff. We've got an O&M team that looks, and occasionally we've seen photos. We just, it's quite horrifying.
It doesn't happen day one. That's the thing. So the guy can bend his cable super tight, put it in amongst the rail channel or whatever, which is a classic one, right? Just within 1 inch, turn it around. And it's maybe 5 years later that rubber or plastic surface of the insulation develops the cracks, the water comes in. But, you know, a guy might do 5 years of installs before he has that hassle.
That is true. Now, 25 kilo panels we're talking about, that's at one end of the spectrum. And how I heard of IECO was, well, I'd heard of them, but I didn't know much about you guys until I saw, correct me if I'm wrong, the Neo 8.6 kilogram panel that was, it's 450 watts, something like that?
Yeah, so the Nebula. Yeah, so we have a range of panels called the Neo Star.
Right.
And within that, we've got Nebula. So all of our, we want to shoot for the stars in our business, right? So everything's
shoot for
like
the Nebula.
Stellar, Comet,
I can see.
You know, when we bring out the next panel, it'll be the Mars or something. But this one, the Nebula, to have that 9 kilo size is just really attractive for things like a donga. Or maybe you've got a cool room where you just don't have that structural integrity to put the 26, 25 kilo CNI panels on there. We can solve that problem for you, as long as it's trafficable, right? Because you've got other considerations, safety, right? If it's made out of paper, this building, maybe the panels can go on there. Can you walk on there? How are you going to deal with that? So you got to think about it holistically. But that's really exciting, right?
It is.
A panel that is at that sort of 9 kilo level that is also enabling you maybe to carry two panels at once. Like there's lots of things you can do.
Well, this is the thing, you know, installer fatigue. It's a horrendous job installing solar panels by hand. People forget that it's hard yakka, and lugging 25 kilo panels or even 20 kilo for the whole day is a killer. So we got this panel. It's 450.
So the panels on market in Australia are 440,
440
and 445.
440 and
so we mentioned before about how when panels come off
yeah,
the line, they've got different
gotcha.
ratings. So we've got 440, 445. It'll be at 450 soon enough, but currently we don't have stock of that yet.
But how do you... I was actually talking with a colleague. Obviously, and you got to correct me, you're taking away the glass. You must be taking away the glass to reduce the weight. There's no other way.
Yes.
What are you replacing instead of the glass? And if it's what I think... What about crazing? What about all that other stuff? So I'm really interested to know. And he wants to put one on his caravan, by the way. Okay. That was Anthony. Yeah.
Oh, right. There is a penalty in the, I think it's the opacity of the material. So basically the transmission of the light through glass is amazing. Almost nothing can compete with glass.
Right.
So the same cells that are making those 475s that we talked about, when you put them with the polymer front side, they're down to 440 in terms of output as a system.
Right.
So if you were to take, let's say, TopCon cells and do the same thing, probably to go to 415 in that footprint.
Mm-hmm.
Some of the lightweight panels on the market are actually physically bigger than ours.
Right.
So we've kept the standard size 1762, 1134,
wow.
that's your 2 square metre.
Wow.
We want guys to pick this up and go, this is just another day. It's just like installing any other solar panel. I can use my Clenergy, my Schletter, my Espire equipment. and put that on there. So if you've got those, Schletter clamps in the truck or whatever, you don't need any special glue or anything. Just put that on. So that's what we think is really beautiful about it, and you're keeping it off the roof whilst not being heavy. So it's a really exciting product as well for applications where you might be worried about vandalism. So you might have a concern of, let's say, smashed glass falling into a water catchment or something. You can put that there. So the other thing is you could maybe pre-assemble 3 panels onto a block. And quick math, if I was to go 3 by 9, that's about 27 kilos. Potentially, if I'm able to lift a 27 kilo double glass panel, maybe I can lift 3 panels together and put them in some situation. Or maybe the crane or the lifting aid can do that.
Well, that's what I'm thinking.
So I'm thinking regional installs, maybe you could do them real quick. So let's say you had a regional community, maybe Northern Territory somewhere where there's a high cost of install. You don't want to be there very long. Maybe you prefab 3 panels together and you chuck them up with a crane really rapidly, compared to if you were manually installing 3, 4, 40 panels that have got glass or whatever.
So you don't think they'd be applicable in a solar farm scenario?
No, I don't think.
Well, because
solar
of
farm,
the efficiency side.
So they are more expensive, right?
Okay.
So if we look at the drawbacks of this product, so I'd like to talk about the drawbacks and the positives. Positive, not very heavy, 9 kilos, right? If we look at the drawbacks of it, it doesn't last as long as glass.
Yep.
So we've got a projected service life of about 20 years.
Right.
The warranty on it is 12 years.
Right.
So if you look at our commercial products, they've got a 15-year product warranty.
Yep.
If you look at our residential, they've got a 25-year product warranty.
Right.
This is 12, right? So it is shorter.
Yeah, gotcha.
The other drawback of it is it is not as strong as the single glass panels.
Yeah, yeah.
It is similar in strength from a pressure point of view to a 1.6 plus 1.6 double glass panel.
Right.
So it does have that drawback.
What about a hail test? Is it like...
Hail's comparable to the panels on the market.
Right,
it's not as good as our 470. So our 470 has a better hail rating.
Wow, that's incredibly interesting, and I think we could talk for another couple of hours. I haven't covered half the things I wanted to cover, but I've learnt so much, Thomas. I really appreciate you coming in. Yeah. Thanks
No
very
worries.
much for that.
All right, thanks, fella.
That's great.